Okay. So we're getting into equilibrium problems, and it makes a lot of sense because we have been doing problems that have led us up to the shifts of equilibrium. Okay, in fact, I'm going to turn the fan off because probably the fan's going to interrupt. Transpiration lab going on there. Okay, so let's get right to it. All right, so we've been talking about equilibrium and how delta G is 0. We learned yesterday that the rate of the forward reaction equals the rate of reverse, and you know you're at equilibrium when the amount of the reactants products stay constant. Okay, we've been through that. So now it's time to use equilibrium. Now, what does equilibrium tell us? Equilibrium questions tell us if we were to start at 100% reactants, I know I love drawing these, at this position, how much will it move forward to get to whatever that equilibrium position is? Okay, so the equilibrium tells us something about chemists is how far by itself will it move forward until the reverse process catches up and you have no preferred direction, and we've got this spot that is temperature sensitive that we learned yesterday, all right, and it's a position that the universe allows that could either favor the products or the reactants. What we learned yesterday from this formula is delta G is equal to negative RT ln of K. And so if something is very negative, that would mean the natural log of K, the equilibrium constant, is huge. And why does that make sense? Because equilibrium is products over reactants, coefficients become exponents, solids and liquids do not apply. There we go. Products over reactants, coefficients become exponents, solids and liquids do not apply. Yes. All right. For a cult. All right, now, so if I am favoring more of my products, so my U diagram would look like this, and I hope you like it. I'm going to favor more products. My equilibrium position is going to be larger. And if I'm favoring more of the products, that means I go, what? In the forward more spontaneously, and it's a bigger negative. So we've been through that. We know it's temperature sensitive. So now we're going to basically get and do some, how far should something go to get equilibrium? And that's essentially what we do with things that aren't very spontaneous. Or I should say, the reactions aren't completion reactions. These are reactions that don't like to move forward that much. We talked about weak acids already. They barely dissociate. Vinegar, which is a weak acid, only about 5% of its acid molecules actually dissociate into a proton. That's a weak acid. It barely goes forward. That equilibrium position is in the reactants. And the one we're going to talk about for the next couple of days are salts that were deemed insoluble. Okay? Case in point, all right, we're going to talk about today like calcium carbonate, which was the active ingredient in Tums. This chalk is an insoluble compound. So insoluble that aqueous creatures like to put calcium and carbonate together to make seashells. They don't dissolve very well. But the real cool part about this is that things that are, quote, insoluble actually dissolve a little bit. We just don't notice them. They do go forward a little bit. Okay, so that's what we're dealing with today. So these are the types of problems that deal with salts dissolving that we think are clearly just insoluble, but they do have some solubility. Well, I'm going to get to that. So let's get started. So the first question, and I'm working on this worksheet here, is they're asking, will a precipitate form if I pour two solutions together? And although you may say to yourself, how does this got to do with equilibrium? It does, and let me give you that opportunity. This is really a Q versus K question. We're going to take some number of ions, we're going to pour them together, and we're going to figure out if the total number of ions that we're pouring together is either in front of equilibrium or behind it. And I say that again, always with a U diagram. If this is my equilibrium, is my Q behind it, which means I'm going to work backwards and will move in the reverse. Or is it in front? Is my Q smaller than K? That's what this question is about. Okay? You may not see that right now, but you will today. So let's just get right after. So what we have here is we have two solutions. Okay, a little bit of review before we go forward, but in this solution of lead nitrate, it's soluble, and they would say it's soluble on the AP. What you really have is lead plus 2 dissolved with nitrate ions. And the other solution, we have sodium sulfate. Well, that means in a beaker of sodium sulfate, I may write it that way, but you need to know that sodium is a group 1 ion, completely soluble. That means you have sodium ions with sulfate ions, and these are very soluble compounds. These are not what we use for that little equilibrium. Now, what we're going to do, my friends, is we're going to pour them together. We're going to pour them together into the same container. And if you remember your solubility rules, or Coulomb's law, would suggest that things that have a higher, what? Charge will stick more coulomically or attract more coulomically something with a larger negative charge. On the AP, you don't have to identify precipitates, they'll tell you. So the problem would read, lead 2 sulfate will precipitate, or could possibly precipitate, because again, the question is, will this mixture cause a precipitate? So you have to realize that potentially, what we could have, potentially, is we could have a solid, okay, of the precipitate, lead sulfate, and then we would have, of course, we have spectators, the nitrate, I'm not going to write them, but we could have the Pb plus 2 ion and the sulfate ion, and the equilibrium that could eventually happen is at the rate of dissolving will equal the rate of reprecipitation. Remember, equilibrium, things stay constant because both pathways have the same spontaneity. All right? Now, so that's the first thing, is realizing that pouring those two things together is about, when or if this reaction is going to occur. So this is how we write all precipitation reactions. We write precipitation reactions this way. We start with the solid, okay? So we're going to take Pb SO4, and that would be the precipitate if it occurs. It's a solid, and it's going to dissociate into Pb plus 2, and that's aqueous, plus a sulfate, aqueous. We always write the dissociation of a salt this way, okay? And the reasoning is going to make sense in a little bit. So anytime I've got a solid who possibly can dissociate into ions, and the ions go back, we start it this way because we want to write an equilibrium expression, or an equilibrium that expresses how well the solid makes products. In this case, the ions. So we want to write it this way, okay? And that's the way you'll see it. And they could say to you on an AP, please write the ionization reaction for lead sulfate, okay? And you would do this. Solid, it's ionic, breaks apart into aqueous ions. They'll tell you it's soluble, or they'll tell you that it will break apart a little bit. Okay, now, what do we do here? Will a precipitate form when I pour these together? Okay, well, first and foremost, we're not at equilibrium when you pour these together. So I want to get a handle of where my Q is in relation to my what? K. Don't forget, keep drawing this. There's a K here. I don't know if the Q is in front or is behind. I don't know if the Q is smaller than K or greater than K. Don't forget that Q has the same formula as an equilibrium constant. It's just not at equilibrium. Q equals K. So what's the formula? Products over reactants, coefficients become exponents, solids and liquids do not apply. So I'm going to write a Q formula here for this reaction, for this ionization reaction. And Q is going to equal products over reactants, and I write the concentration because this is aqueous, so I write brackets because it's going to be a molarity, equilibrium problems are either in molarity, brackets, or partial pressures, parentheses. Okay? Remember that derivation we did? There was no solid, there was no liquid. Expanding of a gas changes the entropy. A solution diluting changes the entropy. And of course, I'm going to times that by SO4, -2. Okay. Now, the question is, what is the molarity of those values? Well, if you notice, hey, they gave me a molarity of the lead nitrate, they gave me the molarity of the Na2 sulfate, but careful, careful, careful. And this we've done before. This is the cool part of the year. We've done this little piece. When we pour solutions together, isn't there a new total volume? So aren't the molarities going to dilute a little bit? Remember a formula we used called the dilution formula? It's called MV equals MV. We're going to solve for the new molarities. Anytime I pour solutions together and I need those new molarities, I would do that. So this is what we used earlier in the year when we did this kind of math, but we didn't do equilibrium. So that's why I'm closing the door. So I'm going to do MV equals MV. Now what I'm going to solve for is the new molarity. So in this case, I have 0.10 liters, and I have a molarity of 8.0 times 10 to the -3, and I'm timesing that together. I want to solve for the new molarity. Now remember, this V is going to be the new total volume. So I'm adding 0.1 liters to 0.4 liters, so I want to know what the new molarity is when the total volume, total, is 0.5. We've done this before, okay? It's going to go down a little bit. Why do I want the molarities? We want molarities for equilibrium problems, because we build K and Q with molarities. If this was a stoich problem, we want moles, okay? So I do 8 to the -3. I'm going to times that by 0.1, which is kind of silly. I should know that answer. And I divide by 0.5. And what I get is 1.6. M is 1.6 times 10 to the -3. Yeah. That's my new molarity. Of what though? I did lead nitrate. So I'm going to plug this in. I'm going to plug this in right here. So this becomes 1.6 times 10 to the -3. Didn't have to be that big of a bracket. Okay. I'm going to do that again for the sulfate. The sulfate said, hey, I started with 0.4 liters. My molarity was 5.0, or 5 times 10 to the -3 molar. And by the way, these are small amounts, okay? And my new volume is, of course, going to be 0.5 because I'm adding essentially 100 milliliters to 400 milliliters, 0.1 liter to 0.4. I'm going to solve for that M, or the diluted form. Okay, so 5 to the -3 times 0.4 and divide by 0.5. And I get 0.004, or I'll just point it as 0.0, or 4 times 10 to the -3, doesn't matter, 0.004. Do we confirm that? Because I do make mistakes almost all the time.
Yep.
Okay, cool beans. Okay, if beans are chilled. Now, let's go solve for the Q. Remember, what is Q? It's some snapshot of time. When I pour these together, how many of each do I have? And comparatively speaking, based on where the K is, it'll tell me if I'm going to what? I'm always moving toward equilibrium. It's going to tell me if I'm going forward or reverse. So let's go find what that value of Q is. So 1.6, second function, -3, big fingers. And times that by 0.004, I get 6.4 times 10 to the -6. So my Q, and it's a cute number, Q, get it? No. Q equals 6.4, come on, Kate, times 10. You love this. -6. You try to hide it from me, but you know you jump for joy. So I got an important value, Q. That's going to help me determine if I mix this together, am I going to make it precipitate? What does that mean? Am I going to go and move toward this and be more spontaneous in this direction? That would make me see it precipitate. Okay. I need a K now, yeah.
Why didn't we divide by the reactants?
Oh, very good. Because the reactant is a solid. Products over reactants, coefficients become exponents.
Solids, liquids do not apply.
Solids, liquids do not apply, but thank you for bringing that up, because if I should have made that point. So that's a good point, as I kind of almost glazed over, okay? When you write these formulas for these types of reactions, you'll never have a denominator, okay? And that's what makes them unique when we solve for the K, and gives the K its unique name. Let's solve for K now, because once I have Q, knowing where K is, I can see if this is going to go forward or reverse. That's what this is about. Everything that we've been doing is about Q and K now. That's Le Chatelier's principle. Okay, now, what are we going to do now? Let's go find K. K is the same formula, doesn't it? So K, or KQ, or equilibrium constant, has exactly the same formula. Products over reactants, coefficients become exponents, solids and liquids do not apply. Q and K have exactly the same formula. Q equals K at equilibrium. When we first put those ions together, we are not at equilibrium. Okay, but we need to know the positions. Let's get there. So they gave me something else which is brand new, and I want you to circle it. They're telling me something called the molar solubility. They're asking for the molar solubility. Anytime you think of molar solubility, they're asking for the molarity of the salt at equilibrium. Now, this is important. In one of these, there's one of these and one of these. So it's important you understand that. So when I'm asking for the molar solubility, we're always solving what we call X, one value. It'll make more sense as I keep going. All right, now, what's really cool about this, okay, this type of K, we call it a Ksp. We're going to learn that equilibrium constants have different names. If they're for acids and how well acids come off, we call them Kas. If they're for bases to know how much they go forward, they're called Kbs. Okay? We had a reaction with water splitting apart. We call that Kw. All right? We call this a Ksp when we have a reaction like this. Check it out. What is K? Products over reactants. We have no reactants because it's a solid. So what are we left with? Oh, the product of the ions that come off the solid. What is solubility? The ability of ions to dissociate from a solid. So it's the product of the ions. Solubility product. So this equilibrium constant, yes, it's an equilibrium, but the way that we set this up this way and write it this way always gives me a measure of how soluble the compound is. If K is bigger, you've got more ions because the ions are always the products. So if the K is smaller, you have less ions and you're not as soluble. So we can actually use the equilibrium constant as a tool to know how much this goes forward or not. That's why we call it a solubility product. Kate, I can see you're jumping with joy. All right? Now, you're forever in my video, Kate. All right? All right? Now, let's go find that number. So what they say was, they said the molar solubility of the lead ions is 7.4 times 10 to the 4th. They said when the reaction reaches equilibrium, we're not where when we finally get to equilibrium, we know the value of the PB is 7.94 times 10 to the negative 4. Now, you did this last night a little bit. To answer this, I need this one. We've been down this road before, you just forgot. One of these makes what? One of these. One of these makes one of these. What's the ratio of these two if nothing else was in water and that thing just broke apart? It has to be 1 to 1. This is the X, and this would be the same value. Last night you had the problem I showed you where it broke apart into two ions. For instance, if I give you this one, PbCl2 would break apart to Pb plus 2, and what? 2 chloride ions. Ooh, if that was the case, I'd have to double that one, because one of these makes two of them. Stoichiometry is always with us. Ooh, stoichiometry. So here it's a 1-to-1, so they have to be the same number. Oh, have we seen this before? Oh, I think so. I think so. Check it out. Remember, a long, long time ago, when we had water and it split apart into a proton and a hydroxide, somehow I did this to it. I said, what if we multiply the molarity of the proton times the hydroxide? It'll equal Kw, which was 10 to the negative 14. This is an equilibrium constant. Oh, by the way, these are aqueous, liquid. Products over reactants. There's no reactants because it's a liquid, doesn't have a molarity. And then I said to you, what number times itself equals that? And you said 1 times 10 to the negative 7. Another way I can say that is, what's the square root of that? And you can find that. X squared equals that. These are some things you're going to see a lot of. So guess what? To solve for that equilibrium, in this case, it's just x squared. Okay? So it's the same number. We've seen this before. It's the fun part of the year because I get to put together things I left behind. So this has to be what? 7.94 times 10 to the negative 4. And we're just going to square that number. And that's going to be the value of your KSP, an equilibrium. Oh, man. You feeling this? I am. I'm going to need a nap after this class. So 7.94. All right. Negative 4, square that baby. And I get 6.3. My KSP is 6.3 times 10 to the negative 7. Okay, party, I'm going to move my U diagram. Hope you guys are getting it. Sorry. So, does this precipitate? I've got my K. It's 6.3 times 10 to the negative 6. I've got my Q. It's 6.4 times 10 to the negative 6. Isn't this bigger? Isn't this 6.4 times 10 negative 6? Isn't that a bigger number? Q is larger than my K. Reaction's always going to work back toward equilibrium. We are going to move and shift where to get to equilibrium? Back to the reactant side. There's going to be a more spontaneous movement or shift that way. Solubility increases or decreases as ions become a precipitate. Decreases, and we would say that in this answer, a precipitate occurs. Now, I did a lot of stuff in here, okay, but let me just tell you what's AP. Write the ionization reaction for the precipitation of this. You start with the solid this way. Do you see why they did the solid? Because they want the ions to be the product, so that the equilibrium constant is a measure of how many ions or the solubility. They would give you a point for writing the KSP formula like that. They would give you a point for recognizing that you had to dilute your molarities as you pour them together. They would give you a point for calculating the Q. They would give you a point for calculating, for filling this in knowing it was the same number. They would give you a point for calculating the KSP. Another point for comparing them correctly to your answer. That could be a 10-point question. Okay? And there's a lot there. Now, see where it says KSP 4 and 5? If I'm losing you at any time, okay, then what you could do, party people, not that. What we can do is, I have some KSP notes. And we can go to skill 4 or 5. You can click on that skill, and I go over exactly what I'm going over just now. So these are this is 100% on your AP somewhere. They may not do all of those components, but let's continue on, okay?
So if the Q is greater than K, it's more spontaneous than
If the Q is greater than K, now let's think what that means. Q is the same thing as K, correct? Q is products over reactants, coefficients become exponents, solids, liquids do not apply. But if your Q is greater than K, that means you have more products than you're supposed to have compared to equilibrium. So the reaction is going to lose those products and work downward.
and be spontaneous.
And so always the reverse is more spontaneous when Q is larger than K. If Q, and think about this for a second, and this is really, really important to understand big picture. Stay with me, I know, it's a long, today is about me teaching, yes. Well, let me just finish my point because I'll forget. See how small that K is? So if I were to draw a U diagram, it would be like this. Where here's my equilibrium. And the reason why I'm drawing it like this is because it's so gosh darn small, this thing barely produces any ions. Can everyone see that? It doesn't go forward a lot. So when you pour ions together, isn't there a greater propensity to add beyond the K? That's why we say that salt is insoluble, because it's hard to put in the number of reactants that it will dissolve in. Look at, we're adding what? 5.0 times 10 to the 3 molar. That's small enough, okay? So it's really hard. So this is, people say it's insoluble because it precipitates most of the time. It's hard to have a Q less than K. Go ahead.
Wait, so, since, like, at equilibrium, since the molar solubility of the lead is that number, 7.94, since there are different amounts of the lead ions and the sulfate ions, why are the two molar solubilities?
Because we're looking at the position of what it would be if I take this solid and just drop it in water. We're finding that spot. And then we're going to take that number and compare it to if I just throw stuff together. If I was already at equilibrium and then I added something, you're right, we would retain equilibrium at the same number, but the values will change a little bit. We'll see those kind of questions. So right now we're just taking, hey, what would be the value if I just dropped the salt in water and it would go 1 to 1 and reach that point? We have that somewhere. Now and that's gone. We did that in a separate test. We know that already. But besides, we know that for what? For a particular temperature. Different test. Just take arbitrary moles of each. Boom. And we can calculate that's still going to be way over. You're right. At the end of this reaction, we're not going to have that. Okay, we have a disproportionate amount. There's going to be some excess, and there's probably not going to be a 1 to 1 back. You're right. So we're just basically saying, what is the value if I drop the solid in and it reaches equilibrium? What's its value? Okay, now we're going to do this. That's what they're comparing here. But there are going to be times where we add extras of something at equilibrium, and you're right, there's going to be some adjustments to that. Okay, moving on. Okay, so let's go and jump to number 3. Okay, so flip that over, okay, 9 times, 1 time, 3 times, okay. I'm not getting a nice light, but I would like it. Okay. All right, so it says calculate the molar solubility. Boom, here's that word again. Calculate the molar solubility. They want to know how much comes off. Solving for X. If the Ksp is 1.4 times 10 negative 11 at 25, notice the temperature they're giving you. Temperatures are important. Temperature change, so does the Ksp or every K. So that's something we learned yesterday. Okay, so this is Ksp skill 2A, but most important, let's do this. So I'm going to write a reaction first. It's really helpful to see what's happening, but I'm always going to write these Ksp reactions or ionization reactions the same way. Okay, so I'm going to take my solid, calcium carbonate, which is our chalk, active ingredient. It was a drug according to, Tums. It's a solid. I'm going to become what? Calcium plus 2 and carbonate, -2, and this is aqueous. Now the KSP for this salt is 1.4 times 10 to the negative 11. What does that tell you? Is this very soluble salt? No, it barely dissolves, okay? Remember, we can use the KSP to really evaluate how much it dissolves. Okay, now they want to know what the molarity is of this. I'm going to write the K equilibrium here. The KSP, it's a KAQ, but for these types of reactions is equal to what? Products of reactants, so it's pretty simple stuff. K is +2. I'm using brackets because I have molarity, aqueous. I have carbonate, -2. And just like I said before, there's no denominator. Why? Solids don't have a molarity. Okay, liquids don't have molarity. I never put them. And by the way, this would be a point on the AP. They would say to you, write the equilibrium expression. Boom, that's it, 1 point. Very simple. What is it? It's a formula that helps us figure out where that position in equilibrium is for a particular temperature. Okay. Now, I want to find what these concentrations are. So I need to do a little bit of math here. Well, I know the KSP. The KSP is 1.4 times 10 to the negative 11.
Square root it.
Yeah, you can do that, for sure. Now, I'm going to write an ice table so you see it. Some people don't see it, and again, there'll be times where I think an ice table, this is an equilibrium ice table, okay? So, so initially, and this is important, we have exactly no products yet. We do an equilibrium ice table. Now, I don't write the solid in ever because there's no molarity, but there's no products yet. So anytime we do an equilibrium, we start here in my U diagram at 100% reactants. We're going to pretend we are forward as all the way we can. Why? Because it's going to go forward somewhat. Maybe a little bit if it's a small Ka, it might be big if it's a bigger Ka, but we know we're going forward, so this becomes minus and this becomes what? Plus X. Now, why are these both the same X? Because it's a 1-to-1. I know it's silly, you see it already, but I'm doing this for people that don't see it. Initially I have nothing because I'm starting with 100% reactants. It's going to go forward something. So this guy would be minus, and these are positive X. Now I'm going to add them to the 0 because this is the change. What's at equilibrium? Of course, it's X and X. And Adam saw right away that they both are going to be the same value. So we plug this in, okay, to the equilibrium, 1.4 times 10 to negative 11. That equals your KSP. I'm plugging them in. It's just X squared. And you're going to see these patterns that come up in a lot of equilibrium problems. It's like it's going to get easy. Now, the one thing I will reiterate is this is not a stoich problem, which means we don't deal with moles, we deal with molarity. Our formulas are based on molarity. That bracket means molarity. Now, if this was gases, we would, and we were using partial pressures, it'd be parentheses, remember that? So we only have gases or aqueous in our Q's and K formulas. So yeah, it's just that, okay? I think you can handle that. We're going to square root both sides. What do you get for X?
3.7 times 10 to the negative 6.
Anybody back that up?
Yeah.
Mm-hmm.
Okay, now what did we just solve for? We solved for the molarity at equilibrium for either one of these two. What do we call that? We call that the molar solubility. And now, I always say it equals X. One of these becomes one of these, correct? So any one of them is the solubility of that formula. And so that is your concentration. So you would say that this calcium carbonate, okay, its concentration is equal to 3.7 times 10 to the negative 6, and it's molarity. Don't forget, we're not solving for moles. Okay, let's do the next one. let's calculate the molar solubility. Here's that word again. That means solve for the x at equilibrium for that formula. If the KSP is 1.7, I'm going to write the formula or the equation, which could be a point. PbCl2, it's a solid. Double arrow. I should have a double arrow up here, sorry. It's equilibrium. It's going to sit in water. It's going to break apart into Pb plus 2. It's an aqueous. This is a point on the AP. Now hold on to your ponies for a second. I've got 2 chlorine. So how many chloride ions come off? 2. So it's going to be 2Cl aqueous. A little bit of a different formula here. Okay. Let's solve for, they could ask you to write the ionization reaction, 1 point. They could say write the equilibrium expression. So I would go what? KSP is equal to what?
PB plus 2.
Yeah, it's going to be brackets around Pb plus 2, because that means the molarity of it times,
2 Cl negative.
well, it's Cl negative, whatever that might be, products over reactants, coefficients become what? Right. That becomes a square there. And there's no denominator because what doesn't apply? Solids or liquids, they don't have a molarity. That is a point. You with me? You have a question? Okay, cool. Please, don't be afraid to ask me. This is the point, like, you get to go back and forth with me today. So that's a point. That's another point. Bless you, meant it. You may have lied about it. At least I was up front about the line. Okay. It's a knee jerk. You know, we taught to bless people when they sneeze. I don't know how that works, though. You feel better because I blessed you?
Yeah.
Okay, cool. Maybe that's the point. She's like, stop talking to me. I'll say yes. Okay. Now, hold on here. So now we're going to do the same thing. And I know probably you guys probably see this already. But what I'm going to do is this. Same idea. Write an ice table. I'm going to start my equilibrium always pushed up against 100% reactant, so I have no products. Hey, plus X, hey, this is going to be, we're going to lose something, but because it's a solid, I can't measure it. So I'm going to go plus X here. What is this? Plus what? What is this going to be? Look at the 2 there.
2x.
Plus 2X. Ooh, in stereo. Awesome. Okay? That's important. My friends in chemistry, stoichiometry is still with us. Woo! There's 2 of these for 1 of these. So this equilibrium table, just like a stoich table, has to express that ratio. Okay. Now, of course, I know it's silly, but we're going to add it to 0, and you get X, and you get 2X. Okay? Now, important. We're going to put this, and understand something, we're going to put this into this expression. And I'll give you a break in a second. Okay, so watch. Here goes my X. This goes 2X. Don't forget it's squared. Now what does this equal? This equals 1.4 times 10 to the negative 11.
Negative.
Now, people get confused. They say, Mr. Grodsky, why do we have a 2 here when there's a 2 here? Because this 2 was due to stoichiometry in the reaction. This 2 was due to the derivation where we did a logarithmic function where the coefficient becomes the exponent. Entirely different reasoning. We are measuring changes of entropy in this to know if we're going to shift forward and reverse. There are 2 different reasons. Well, we're going to times it by 2. What if to square it? Because this is the stoich. Last night, I gave you the molar. I gave you the molarity of this salt. That was a 2 to 1. What was this? Wasn't it 1/2? We had to cut it in half because of stoichiometry. All right. Any case, real quickly, how do we clean this up? this becomes 4x squared, times x, this becomes 4x cubed. This equals 1.4 times 10 to negative 11. I'm going to divide by 4. How do I get rid of the cubed? Baby root. I'm going to cube root it. So I'm going to take 1, for those that can't see, sorry. I'm going to take 1.4 times 10 to negative 11. It's equal to 4x cubed. Divide by 4. And then we're going to cube root both sides to solve for x. So I take my 1.4.
Mr. Ksp.
Did I forget something?
1.7, not 1.4.
It's 1.7. Thank you. Ooh, I appreciate that so much. I only got like hate responses. As you know, it was 1.7 10 minutes ago. You should know better. Okay, thank you. You get so much negativity on the internet.
To the negative fifth, not negative 11.
Oh my gosh, I'm looking up here. You're right. Yep, thank you so much. 0 for 2. Okay, if you're screaming out there, I finally fixed it. Okay, 1.7, so thank you so much about that. Times second function, e to the negative 5. Divide that by 4. And then I have to go to what, the math function? My calculator?
Math 4.
Yeah, math 4. Second answer. And I get what? 0.016. What did I just solve for? The molarity of my Pb plus 2. I solved for my x, didn't I? That is the molar solubility. Now, if I wanted the solubility of chloride, it would be what? Times 2. But that's not the molar solubility. For every one of these, I produce 1x. So if I was asking for the molar solubility, I'm solving for x. Because there's 2 of these per one of these. The molarity of the chloride ion is always twice the molarity of the salt. So we solve for x. Okay, of the 2 salts, who is more soluble?
PbCl2.
Yeah, because in PbCl2, the molar solubility is 0.016, and for calcium carbonate, it's 3.7 times 10 to negative 6. Now, one more point here that I want to make before I give you a little break. Okay? When we compare KSPs, we can compare solubilities mostly if they have the same formula. Let me talk about this for a second. Let's say I had silver chloride, which is pretty insoluble. It's going to have a KSP. And what if we had copper chloride? Now, just stay with me for a second. I'm making up some numbers. What if the KSP was 1 times 10 to the negative 8? What if this was 1 times 10 to the negative 5? Clearly that's the right answer. That copper chloride is more soluble because it has a bigger K. It favors the products more, correct? So you may say, Mr. Grodsky, why did we do all this math to compare the solubilities? Because they have different ratios. If this is AgCl and this is PbCl2, you can't just look at the KSPs because they have different formulas. This is x squared equals KSP. This is 4x cubed. You have to solve for it if the ratios are different. 99% of the time on the AP, they'll give you the salts with the same ratio, like a 1-to-1. And they'll say who is more soluble. You look for the bigger what? KSP. If I give you acids and who's a stronger acid, higher Ka. It's the same idea. Remember that? Okay, we're going to take a small break. So the next question says, which salt is more soluble? Again, let me reiterate, okay? They love to do this, and this is easy. KSP, the way that it's written, larger the KAQ for these reactions, the more ions. Okay, now look at the values they gave us, and please make sure I have the right numbers. They gave me what? calcium carbonate, and they gave me the KSP was 1.4 times 10 to the negative 11. And then they gave me PbCl2, which is kind of weird. I gave myself because I wrote these problems. Okay, and the KSP is 1.7 times 10 to the negative 5. Now, if you eyeball this, you'd say clearly lead chloride is more soluble because its value for KSP is so much bigger. And it winds up being that, but you can't compare salts that have different formulas or different ratios. You have to actually solve for it. And when we do, we actually get a number that's reflective of the difference. 3.7 times 10 negative 6 is the molar solubility. Okay, whereas it's 0.016, so clearly lead is more soluble. But as I said before, if they give you a list with the same formula, like in this case, what if they give you iron chloride, a 1 to 2, and now they give you the KSP to be 2.0 times 10 to the negative 5, this would be more soluble. I don't have to do any math because it's the same 4x cubed formula. So they normally give you that, and it's just an easy concept, really. But if they throw a curveball, okay, which they haven't been doing the last few years, you have to solve for it. All right, so in any case, the next question says, which is more salt is more soluble? Hey, very simply, lead chloride has a higher molar solubility. If you were comparing a KSP chart and they had the same formula, then you would say, in this case, iron chloride, iron 2 chloride, because it has a higher KSP, thus more products are favored at equilibrium. Yes?
Could you also say that the calcium carbonate has, their ions have higher charges?
Well, if they said to you, and this, I love what you're doing right there, because they'll do that in other ways, but they'll direct you. They say, explain the differences in the KSP in terms of, let's say, Coulomb's law. Then they're asking you to say, oh, these don't exist as free ions because they highly attract each other because of the, so yes, they do that stuff, but they'll say it, they'll come out and say in terms of. Yes?
What does the molar solubility represent?
It represents a molarity of how much that solid becomes an ion. I always say X because here is one formula, and it breaks apart into one thing. That's the same solid. Isn't this a 1-to-1? So whatever this X is how much that breaks apart. In this case, we had lead, I got rid of it. We had lead 2 chloride. One of these makes 2 of these. So 2 times the X is not the molar solubility. In one of these, you make one of these, that's the molar solubility, how much it comes across. It just, yeah, that's all it means. So I always say solve for the X, and that's your molar solubility. Okay, let's go on to the bottom question, the last one here. All right, let me just do race, and race. All right. Now, if you notice in all of these questions, what was the temperature?
2500.
Right. Okay, and here is my connection from yesterday to today. Now they're saying, and they won't come out and say it, but subtly, hey, calculate the new KSP for the molar solubility of lead chloride, okay, when the molar solubility now is this. Notice at 30, everything we just did in the previous problem was at 25. We just changed the temperature. Ding, ding, ding. Once the temperature changes, the equilibrium position changes. And that equilibrium position changes based upon if the reaction is exothermic or endothermic. That's what we did yesterday, and here we are applying that concept in an equilibrium problem. So, what are they telling me? Well, this is easy. Again, I know I erased it, but lead chloride, I keep writing this so you can understand it. I know you have it in your paper, is lead plus 2 aqueous plus 2 chloride ions, aqueous. Okay, now, what's the KSP? Well, KSP, very simply, for this one is going to be the Pb plus 2 again. And I'm just rewriting stuff we already had. And then we have the chloride ion, and we have this squared. Now, they're giving me the X, because they said the molar solubility was what? 1.78, yes? So they're giving me the X, not this one. Remember, this is 2X. There's 2 of these. So they're giving me this number here. So, my purple go. Okay, so this is 1.78 times 10 to the negative 2. I think that's, I don't know.
Wait. If it's, cause in the other one we did the KSP, we like made that like the equal vast, and this one it's like the KSP is one of the variables.
They want you to calculate the KSP. We don't have the KSP here. So you're right. In this question, they gave you the KSP. And by the way, there's only 2 questions. They can either give you the KSP, you solve for the X's or 2 X's, yes? Or you have the X's and you solve for the KSP. There's 1 of 2 ways in these questions. So this one's going the opposite way. So they're giving me the X. Now, just like, well, not quite like last night. Last night, they gave you this guy, which was 2X, and we divide by 2 for this one. Now I'm giving you this one. What is the value for the chloride ion concentration if the X is 1.78? I know this is my X, this is my what? My 2X. I gotta double it. For every one of these, there's 2 of these. They're giving me this. This is 2 times that. And not only is it 2 times that, what's my formula have? A square. Why am I doubling it and squaring it? Because for 2 different reasons. This has to be doubled because it's my 2X. This is my X. They gave me this has to be double. If I throw lead chloride as a solid in water, there'll be 2 chlorines for every 1 lead to reach equilibrium. Okay? And so, party people, we can now solve for KSP. So I'm going to take 1.78, 1.78, second function, e to the negative 2. Times 2, square it, times it by 1.78, and let's go e to the negative 2, and I get 2.3 times 10 to the negative 5. That's my new KSP. Everything we're learning just applied. What was the K before? What was the K that they gave you? It was 1 point, what was it? What was in the problem number 4? What was the KSB? 1.7. 1.7 times 10 to the what?
Negative 5.
Negative 5. Was it that?
Yeah.
Okay. Now this is 2.3 times 10 to the negative 5. It got what?
Bigger.
Yes. Remember this? The equilibrium shifted where?
Right?
Yes. Now it got bigger. Your KEQ, KSP is increasing. If it's increasing, it's favoring more of the products or the reactants. The products are more favored. We're shifting the equilibrium into the position that when equilibrium is now established, more products, more ions are going to come off the salt. The second part of the question Is this solution just means, is it an endothermic or exothermic when this dissolves? Is this reaction endo or exo? What did I teach you yesterday? If we increase the temperature, the reaction is always going to go in favor of the endothermic or the exothermic pathway. Right, if you increase the energy, you're going to feed the endothermic pathway. So by me knowing it's going to the right, I know in this reaction, the heat is written here. Or the delta H is what charge for endothermic reactions? Starting low, going high. Delta H is what? Positive. Temperature of the environment goes what? Down. The solution's going to get cold. It's taking energy from the environment. All the things you learned. So this is an endothermic reaction. This is what we did yesterday, now applied to an equilibrium problem. Hope you see that connected. They love to ask that. They love to say what happens to the value of the equilibrium constant when temperature changes. You have to know if it's exo or endo, or in this case, we figured out it was going forward. We knew the temperature was increasing, so we knew the endothermic pathway was this way. If I decrease the temperature, that thing would go this way, wouldn't it? And why? Because if you decrease the temperature, it would favor the exothermic pathway, releasing heat. Okay, they love that question. So understand that K and Q can change. All right, and also great, Lily, they went backwards. They were solving for the KSP given that, okay? All right, now, I want to teach you one little thing, and the rest of the time, you're going to work on your homework problem. That's to put homework problems, but you'll get pretty far. So I want to talk about one problem here. So flip this over back onto the first page. I want to talk about number 2. It's an equilibrium problem. It's an equilibrium problem, although it's not a KSP. This is not a salt, but I want to be able to look at this, okay, with a fresh lens, but use the same skill sets. Okay, now, I have an ice table already written, but I want to explain some things. So look at here, Lily. At 2,000 degrees Celsius, the equilibrium constant for reaction, they call it a Kc. Kc just means we're going to use concentrations. Even though they're gases, we're going to use their concentrations. We can use molarity for gases. Okay? Now the first question they would say is, write the equilibrium expression. So we're going to say Kc, which is a KQ, and it's products over reactants. Coefficients become what? Coefficients become? Right. If you don't have that there, it's wrong. Yeah.
What if they read parentheses because it's a gas?
Okay. We can treat a gas like a molarity, right? If I have a 10-liter gas container, and I know there's 2 moles in that container, 2 divided by 10 is my molarity. So I can have molarities for these. If you notice, there's a molarity given to you. So knowing there's molarity with the gases, I know I'm using brackets and molarities. Now, if there was partial pressures given, this would be called a Kp, and this thing would be the same except you'd have parentheses. You're right. But because they're using, so gases can have molarities and concentrations or partial pressures. That's a great question. Okay, that's a point. That's easy, guys. That's a point. Now, they're giving me initial concentrations of the no. Is point 2. They want to know what the equilibrium concentrations of all 3 gases. This is not a Stoich table. Stoich tables are what? Are going to run 100% and run out of something, and you have a limiting reagent. These are equilibrium. They're going to go forward a little bit and then reach, or a lot of it, depending where the equilibrium is. So we always do them the same way. Start with 100% reactants. That means you have nothing made yet. And if you always start from this position, you know you're gonna go forward a little bit. It's gonna be, so this is gonna go minus something. But wait a minute, there's 2 here, so minus what? 2x. These have 1, so these are plus what? And the reason why they're plus, guys, is because in this position with 100% reactance, I can only go forward. So plus x. And they're plus x apiece. That's my change. Now, at equilibrium, this is 0.200 minus 2x. This, of course, is x plus 0. Put down your calculator, you get that. Let's plug it in. X squared, that's easy. X times x. Here's where it gets gnarly. 0.200 minus 2x, and don't forget, we've got to square that. And that equals the value of Kc, which is 2.4 times 10 to the 3. I have to solve for x, and I can figure out how much at equilibrium. So my friends in chemistry, all right, if we were to do a little bit of simplification, everyone can see that we come up with a what? A quadratic formula. And if this was college chemistry, you'd have to figure this out. But in AP chemistry, they don't do it. They don't give you this problem. So you're never going to run into the quadratic equation. You know what's making us run into the quadratic equation? This minus 2x piece right here. This is causing us all kinds of headaches. Let me explain, because we're going to see this coming up shortly. We deal with equilibrium problems that the K's are extremely small, either weak acids or solids like today that barely dissolve. Stay with me. If the K's are really tiny, look at my U diagram. If the K's are really small, the KSPs, all right, how much is it possible to go forward? It's really hard for the Q to be less than K, isn't it? Because that's such a small amount, correct? So we mostly live in this area where we work backwards, precipitation. Okay, does that make sense? So because it barely goes forward, this change of x is nothing compared to this number. It's insignificant. So what we wind up doing is approximating this away. And now that's solvable, isn't it? Okay? Now in this problem, it would not be appropriate because our k is too big. But we're going to live in a land where that's a negative 3. So if this problem was the same problem that was a negative 3, I'm going to take that away, and then I could solve for this and get my x, square that, times it by that square root, and we're there very simply. And the cool part is, when you compare the values of running a quadratic, for the small ones anyway, rejecting the one that gives you a negative number and plugging back in, what you get from approximating is the same number. Because it's going to be 0.000037, that's extra. Because this little x is so small compared to that value. So we're going to run into those. I call this the quadratic catastrophe. If you run into it, you say to yourself, oh, I got to approximate away that x. And we'll see that. Okay, the rest of the time, I gave you a new worksheet, okay? And I want you to do A. Oh no, I want you, what did I give you? Hold on. I gave you 5A, correct? No, what did I give you? Just 5?
Whatever this is.